Hi everyone, my name is Fernando Pereira, and today I will talk about Fusion, a compiler optimization that became very common in the context of tensor compilers. To explain what this optimization is, let us consider a well-known operation in transformers, the single-head attention function. Single-head attention is one of the core operations in transformers, which are used to train large language models. This operation was introduced in this paper by Vaswani et al. And is perhaps one of the most important milestones in the recent history of machine learning. The function is relatively simple. We can see its formula here. It involves two matrix multiplications plus transposition, scaling, and softmax. If we had to represent this operation as a computational graph, we would have something like this graph here, which receives as input three matrices. These are the matrices K, Q, and V. We can implement single-head attention very easily in a library like PyTorch. Here's the three-line implementation. So this code implements the computational graph that we see on the bottom. Something to notice is that perhaps we could replace some of these combined operations with a single fused operation. In this example, I'm assuming that we could have an operation that combined matrix multiplication with transposition of the right parameter. This operation would fuse two of the operators in our original computational graph. Fusion, in this case, is likely to be always good, for we are not really increasing the amount of data that we need to keep in memory. Before fusion, we still had to keep K and Q in memory. After fusion, these are the matrices we need to keep in memory. So in terms of memory requirements, fusion did not change anything. But we could fuse all the operations too. In this example, we are combining all the kernels into a single kernel, which is available in the Flash Attention library. But now we need to keep all the matrices in memory if we want to implement this operation of single-head attention as a single kernel. When I say keeping data in memory, I'm referring to the fast memory that's part of the memory hierarchy. Usually a computer architecture is organized around a hierarchy of memory. We have fast memory that's kind of very limited, and we have slow memory that bounds. And we want to keep in the fast memory the data that we touch more often. The idea is that we can fit the data in the slow memory. At least most of the time in reasonable applications. However, we might only be able to fit so much data in the fast memory because the fast memory is more limited. Then, if Fusion forces us to have more data resident in memory, we end up having a lot of data transfers between fast and slow memory. This is a behavior that we want to avoid because these transfers, they are slow. So, that brings us to our first observation about Fusion. This transformation usually improves performance, for reasons that I will explain soon, but improvement does not really happen always. We may have regressions too. And deciding which operators to fuse is a challenging problem. Sometimes by fusing some operations together, we forego the possibility of fusing others. The thing is that there are many fusion decisions that we could take when we generate code for a computational graph. These deep learning models are all implemented as graphs, where the vertices represent operations that we perform on tensors. These operations are sometimes called kernels. The edges represent the flow of information about these operations, like when a kernel produces a tensor for another kernel. As an example, this figure shows ResNet 18, which is a well-known neural network. Its observation brings us to the key question. Which operators does it make sense to fuse together? Well, first, notice that we want to fuse operators that are related by a produce-consume relation. For instance, here we have a kernel that multiplies two matrices, and the resulting matrix is later on added to another tensor. So it makes sense to fuse these kernels because one produces data, in this case the matrix C, which the other kernel will consume. Fusing them, in this case, is also possible at the binary code level because these kernels consist of loops ranging on the same intervals. This means that we can merge these kernels using loop fusion, which is a node compiler transformation, which has the benefit of reducing the amount of branches and also increasing the locality in the program. And it allows even materializing data, given that we don't have to send it back and forth in between fast and slow memory. But again, notice that now our fused kernel will need to keep 3 matrices resident in memory, whereas before we only had to keep 2 at a time. The last fact brings us to our third and final observation. Fusion, when seen as an optimization problem, is guided by a cost model. A cost model is a way to estimate the running time of a program. We can do it via profiling, for instance. It is a dynamic cost model built over a profiler. But we can also use an analytical function to do that. Static cost models are functions that try to predict program behavior based on the features of the architecture where these programs run. There are many different static cost models. For instance, here we can see different performance surfaces produced with the cost model proposed by Olivry in 2021. In this case, we are varying the size of the tiling factors and plotting the predicted performance. Here are surfaces produced for similar programs, but this time using the cost model adopted in the XNNC compiler from Cadence Design Systems. This cost model is briefly discussed in this paper, the Droplet paper, by Kaneski et al. From 2024. But the fact is that, given a cost model, we are back into the problem of deciding which operators in a computational graph we should fuse. In other words, given a computational graph plus a cost model, we want to find a sequence of operator fusions that minimize the cost of running this graph. This problem is difficult to solve because if we fuse 2 operators, then we might prevent the fusion of other operators. Also, the order in which we fuse the operators is important. The cost model usually will not be associative when applied onto fused operators. Thus, some typical approaches to find the best sequence of operator fusions will be exponential, as they evaluate all the fusion candidates exhaustively. That's the case of the algorithm proposed by K et al., which does backtracking to try all the fusion possibilities. They use a memoization table, like dynamic programming, to reduce the cost of evaluating all the potential fusion sequences. A different approach was proposed in the Tensor compiler. In this case, the compiler uses an evolutionary algorithm to decide which operators to fuse. But notice that this algorithm proposed by Zhang et al. Is not guided by a static cost model. Tensor effectively runs the computational graph to measure the benefits of the transformations it carries out. Finally, there is also the fusion algorithm that's used in the XNNC compiler, which is based on the same principles that guide the minimum spanning tree algorithm of Dijkstra. In this case, operators are fused greedily until fusion becomes no longer profitable. Anyway, there are really many ways to perform node fusion. This video has only touched the tip of the problem. And if you want to know more about it, I recommend this paper, Fusion of Operators of Computational Graphs via Greedy Clustering, which explains how operator fusion was implemented in XNNC, which is the compiler that translates deep learning models to Tensilica's digital signal processors. So thank you very much for your attention, and I think that's it.